Right, kia ora everyone. Welcome to the first of our energy series for the Bay of Plenty this year. Let's see. Oh, yeah, there we go. Might need another clicker. There we go. So welcome. My name's Mike Pond. I'm going to be your MC for this evening, and I'm a principal in the industrial team here at the local Beca office. Energy storage, is it a game changer? I'd be interested to talk to a few of you at the end of this over a drink, see if you agree or not. But it's certainly going to be becoming one of the more prominent parts of our energy mix, and one of the things that, by the turnout here, we've had a really good response to this event. So it seems to be a topic that's of a lot of interest for various organisations around the place. So in 2024, Priority 1 started this Our Energy Future work. And why did they start that work? Part of it was about they were involved with a number of different forums and initiatives around energy, and noticed there was a bit of a disconnect between some of the different industries about how they were thinking about energy. A couple of examples is, industrial process heat is really reliant on natural gas, which we all know what's happened in the last couple of years around that. Transport and logistics is critical for the economy, particularly here for the Bay of Plenty with the Port of Tauranga here. So through some of that, they decided there was an opportunity for a bit more of a coordinated view around the Western Bay of Plenty's energy future, and I got involved helping them with that initial report. Some of that work, we did some forums where we got various different organisations together across the energy spectrum to look at, what were people imagining in the future? Where were they hoping their organisation would go, and what are the barriers to achieving that? And there was a few themes that came out of that. One of the key themes was uncertainty. It was uncertainty across just so many domains. There's uncertainty around the technology, around the financial implications, around policy, there's political uncertainty. So you add all these uncertainties together, it makes it really hard to make progress when there is and make a decision when there's uncertainty on so many fronts. Coordination and collaboration is another theme that came up, that there was a real opportunity for us to be more coordinated and collaborate more across industries. And that's going to be really important. If we're going to chart a successful path into our future in energy, we need to be coordinate about how we go about it. We need to be efficient, and collaboration is going to be important to that too. Another thing was that energy is not just an enabler, but it's an opportunity potentially for the region here as well. And one of the reasons we've picked energy storage as one of our first topics is that resilience is something we need to think about as a region as well. We're a net importer of energy, various forms into the region, so we need to think about, and particularly with, the effects of climate change and other events, the global events, how much resilience do we have within our system. So a couple of the actions out of that report was to do the Regional Energy Summit, which was hosted last year and was, exceeded our expectations in terms of the interest in that event, and also form an energy leadership group, which I've got the privilege of chairing. So through that energy leadership group, there's some of the people in the room here, part of that group. We've developed a bit of a work plan that we're working through. A couple of the initiatives we're working on. One is collaborating with the University of Waikato to develop a regional energy model to understand what could different futures look like and what are the implications and what are the opportunities for the region. And we're also, another was sort of fortuitously actually, on the theme of collaboration, we had an idea to do it in a series a bit like this, but also at the same time, the EMA and ECA also approached us and said they were interested in doing an event such as this as well. So on the theme of collaboration, actually the four of us, 4 organisations have got together to organise the event for you this evening, and there is more energy events to come, so please look out for those. The next one is planned to be about biomass in August. And why is Beca involved in this? For us, we we work across a number of industries across the spectrum, and we feel there's a real opportunity to bring some joined up and sort of systems view thinking about how we approach energy across a number of fronts, not just electricity and gas is a couple of the things that we think about front of mind, but energy is broader than that. It touches everything in our economy and in our lives more broadly. So first I'd like to welcome up Alan McDonald from the EMA. He's going to give a bit of an introduction to EMA's perspective on energy, and then from there we'll get into the presentations.
Thanks, Mike, and thanks for the opportunity tonight. We've been working quite closely with Beca over the last 2 or 3 years, particularly around some of the energy stuff, and also with Priority 1 on the regional plan, which of course you guys got the money. In Auckland, we didn't get any money for our regional plan, so well done you guys. Why are we here talking about energy? So I guess it's in the name. The EMA is the Employers and Manufacturers Association. About 20% of the country's workforce work for our members. Electricity, depending on what kind of business you're in, it's somewhere between 1 and 4 in your costs. And so the kind of uncertainty that Mike's referred to, we've had businesses 3 weeks away from shutting their doors because they couldn't get a gas contract. We've had others facing 20, 30, 50, 70% increases in their electricity contracts. So where's the future going? What are we looking at? I was working for an EDB quite some time ago now when they were looking at a 1 megawatt battery to service a fairly remote community in Auckland, because that meant they didn't have to string another line. And then you look at the photo that was up there before, we're now at kilovolts storage and things like that. So how does that all work? What's that mix? And one of the things, we've got that energy trilemma going on, but we're really concerned that successive governments aren't really looking at some kind of coherent plan. What's the future of firming? Where does storage fit into the mix? We're looking at deep bore geothermal. That could be quite promising. We've got geothermal assets that we're not using the most of. We've got a network that needs to be fully built out, but there's constraints all over the place, whether they're regulatory or financial. How are we going to do that? What's the roles of EDBs in encouraging things like the use of stored electricity? And those little local distributed networks, how's that going to work? Because storage is a critical part of that. So we're deeply involved with government and others around what does that energy future look like. We've got the Energy Minister coming into our place in Auckland on July 23, so if any of you are Auckland based, if you're members, that's free. If you're not members, you have to talk to me and see if I can sneak you in. But we've got a lot going on. We've got the Prime Minister and 3 of the other leaders also coming in at the end of the year, at the end of September, as we get near the election. And energy is right up there on the top of everyone's agenda for those political parties around what is the future of it, how's it going to look, how are we going to fund it, what are we doing to encourage business? Because we've gone from an environment where we had plentiful electricity that multinationals came here for to an environment where it's routinely cited as one of the reasons our businesses are closing. And that deindustrialisation process is ongoing and something that we're also very concerned with. So the whole electricity future, the various components of it, that's something we want to see addressed much better in the future from a political point of view, which is our interest in that, to support manufacturing. And alongside that is the resilience piece. Right? So other countries around the world are doing manufacturing plans to keep critical industry in their countries so that when things go wrong, like Mr. Trump might declare war on Cuba tomorrow, so what's going to happen there? How do we absorb those shocks? What industries do we need to keep? Do we want to give away, say, critical manufacturing capability like urea plants or something along those lines? Is that the kind of stuff we want to do? So all of that, it's all interlinked. Energy and manufacturing, just you can't do one without the other. So that's the piece we're working on. That's our interest in this. And I'm really interested in just hearing today on where that storage piece of that is going and the future events that we're having. So thanks very much for the opportunity. The wooden spoon's gone up down the back. So if you're a speaker, there's a wooden spoon and a red sock. If you get the wooden spoon, you've got to go faster because Sandra's going to hit you with the red sock otherwise. So thanks, everyone.
Thanks, Alan.
First presentation is from Eric Walters from PowerCo. So Eric is a seasoned electrical engineer with more than 40 years of technical and managerial experience across a range of power generation, transmission and distribution technologies and organisations. So he works for PowerCo and undertakes private consulting assignments in his spare time, specialising in renewable generation, technologies and connection assets. So welcome, Eric.
Thank you for that great intro, Mike, which I wrote myself. Just let me boot this up. I just want to have a copy of the presentation up on my laptop so I don't have to keep looking back at that one. Just give me a second. All right, so we're going to be talking about battery energy storage and how it fits in. To introduce you to PowerCo, we are the second largest electricity distribution business in New Zealand. We are currently looking at buying a network over on the east coast here, First Light Network, and that'll bring us closer to being the number one, but not quite. Vector will be there first. So you can see we've got a lot of interconnection points on the network, and increasingly we're looking at non-network solutions like batteries to help us support the network, given that there's constraints all around the place. Why is that going? There we go. So what is a BESS and how can it be used? The first picture you can see there is actually a standby battery system that we installed at Whangamata. So Whangamata has a single 33 kV line coming into it. When the weather disrupts that power supply, especially during summer when there's a lot of when the influx of population is huge, that whole CBD goes down and it affects the viability of the whole town really. So we put in a standby battery system backed up with a diesel generator. So the batteries are in that container, 40-foot container at the back. Then you've got your inverters and power electronics and control systems in there, and there's a diesel generator at the back. Switchgear building and transformers up there in the front. So that's a 1 megawatt, 2 megawatt hour system. And then of course, you've seen now the ubiquitous car charging stations that are appearing all over the place. But of course there are many more applications for batteries. I'll spend a little bit of time on this slide just to describe where we see the uses of batteries. So the first one is in peak demand reduction. If you can shift the load from the middle of the day, or shift the solar generated power from the middle of the day towards the peak in the evening, then you've got the chance to reduce your power bills, but also you can avoid the need for a higher capacity grid connection, for example, because you can reduce the peak, and if your grid connection is presently is designed for your current peak and you want to increase your electrification, then one way to avoid having to upgrade your connection is to put a battery in. You reduce peak line currents, maybe you save some money. And when we talk about energy arbitrage, we're talking about buying low and selling when it's high. But it also applies to the situation where if you've got excess solar during the day, rather than sell it to the grid at 10 cents or whatever you're going to get for it as a feed-in tariff, save it or store it in a battery and release it later at night to avoid the need to import electricity at 30 cents or 35 cents. So that's arbitrage. We have the backup power, which is what I showed you with Whangamata. Flexibility markets. The batteries don't need to actually discharge much to support the network because of the power electronics. They can change power factors and they can rebalance phases. They do all sorts of magic. And one of the case studies I'm going to show you later is precisely used for that. And then, of course, it's just shifting power from one time of the day to another. So let's have a look at some case studies. We're just going to look at two, and that applies to primarily, where should I be pointing this thing? There we go. So the first one is we've got a big rooftop solar installation at our premises in New Plymouth, at the PowerCo premises. It generates it's more than 200 kilowatts, and it actually, there we go. So you can see that it's sized pretty well. This is a day in January this year, and the light green is the solar generation, and the orange tip at the bottom is the amount of excess generation that we exported to the grid. But you can see on this particular day that we've highlighted, the solar generation almost exactly matched the consumption at the premises. But the interesting thing here is you can see that there are some quite sizable orange tips. And if we had a battery in there, you could shift those orange tips. Instead of exporting to the grid at low tariff rates, you could push it into the areas where we don't have enough generation to cover off the import. And so you're displacing generation that would otherwise be imported. But you can see here it's a pretty good installation, but it could be enhanced by battery. So you've got direct consumption of 150 there, you've got a grid feed-in of 48, that orange bit. So, and the total generation of 200. So that was a good day. Now naturally, and we'll talk about this a little bit later, you can't shift power from one season to another. So in the winter, we wouldn't expect the same performance from the solar farm. And similarly, you wouldn't be able to charge the battery completely from the solar farm. You would need some power from the grid. Right, our second case study is, I don't know if anyone here lives in Greerton or nearby. You may have seen these pole-top BESSs around the place. When there's infill housing or when there's uptake of EV charging or solar panels on roofs, it can cause congestion in the network and voltage control problems, as some of you may know. Now, the usual solution is to, where is this going? That one. So the usual solution is to upgrade the network, so increase the cable size or overhead conductor size, put some new transformers in. They're 250 kVA at the moment. We would put 300 kVA transformers in. Naturally, it costs a fair bit of money and it takes some time to implement, especially with long lead time items. But instead, we decided to put some pole-top BESS in. So the BESS stabilises the voltage at the furthest end of the network. So we're getting one or two complaints from houses who were having appliances not working properly because the voltage was too low. So you could boost the voltage by putting this little 200 kVA BESS in place in strategic locations on this network. Now that had a good benefit because it stabilised the voltage there. It allowed us to defer investing in capacity upgrades. And the good thing is that we can repurpose them later. So maybe in a few years when we do upgrade, we can shift this to another location where they're needed. So in terms of application, am I going for time there? All right. Okay. Just point out that batteries are not a silver bullet. They won't solve all of your problems, but they're going to it's going to particularly suit industries who need to shift load for one reason or another. If it's to reduce costs or if it's to meet a peak at a time of day when you're having to pay premium prices for power, or it's to optimise your use of solar, which might be generating during the day when you're actually not needing power and you're sending it out to the grid at minuscule prices. There are certain things to consider. So capital cost is one. Although the price of batteries has come down, the price of inverters and the power electronics associated with the batteries is still reasonably high. So it's becoming easier, but the economics of these projects can be hard to get across the line with your shareholders. And then there's resilience and duration limitations. Of course, most of these batteries will run for a couple of hours, but what are you going to do after that? There's supply chain considerations, although there's a lot of options out of China now. Fire safety requirements, I think someone's going to talk to that later on. revenue certainty, as I say, you can't shift power from one season to another, so you can't expect the same return all year round. And if you're considering batteries as a solution for your energy supply needs, just think about what problem you're trying to solve and how often will the battery cycle. Remember that you need to import or derive power to charge these batteries before you discharge them, and the efficiencies aren't 100%. You'll only get 90% out of what you put in because of heat losses and so on. Look at what value streams are available, and it could be that you support the local networks with some flexibility services. PowerCo actually is going to tender periodically for services like someone's battery at a premises to help support voltage so that they can defer upgrading a network. So it could be that you're buying and selling into the electricity market, or you're using it to offset your own electricity usage and reduce your costs. So think about those things. And when we talk about grid connected or behind the meter solution, when you're grid connected, you have to pay someone to transport that energy somewhere, whether it's to another facility or even back up through the line and back to your factory. You're still having to pay to transport that power. So if behind the meter installation avoids the need and it improves the economics. So that's what we mean by that. Okay, so the key takeaways are we've got rising electricity prices. We've got some uncertainty on where the electricity prices are going. We have increasing demand changes and charges. We've got growing solar adoption, and often that solar occurs in the middle of the day when it's not 100% utilised. We've got a gas transition, and some industries need to transition from gas to electricity to remain viable. Battery economics are improving, but just remember that there's an entire installation that needs to be catered for. And of course, we're looking for greater energy resilience. So backup power is one solution, but another solution is just being ready to keep your industry operating when there's interruptions to supply. And that could be, if it's only going to work for 2 hours, it might be just to give you a safe shutdown period, for example. And if any of you are from the pulp and paper industry, continuous power is really important, else their pipes clog up and it costs a fortune to clear them. So it's this kind of thing that we need to think about. So if you do have any questions, and we have a great customer team, Clay's here today, who heads the customer team in Tauranga, and they're happy to talk to you about battery solutions. They may refer you to my team, the business development team in PowerCo, but one way or the other, we'd love to have the conversation with you. That's all from me. Thank you.
Thanks, Eric. So next we've got Nikk King. So Nikk is the Director at Active Power and Controls, and has 25 years of experience in control systems engineering and project delivery, and specialises in the supply and delivery of BESS and microgrid applications. So the idea here is we've got two presenters on BESS bringing a couple of different perspectives, so Nikk brings that BESS supplier perspective to this conversation. Welcome, Nikk.
Okay, can we hear me? Right, I'll just go forward. Okay, so I've got Gus here as well down the back, and the dapper gentleman in the hat, so he's going to help me out as we go. What do we do? Active Power and Control, we supply battery solutions. So we're looking for, we call them small batteries, but compared to most of us, when we think of batteries, we think of our home batteries. So the battery scale we're talking about is sort of, 1 megawatt to 20 megawatt size batteries, which I'll show you some pictures of what that looks like in a moment. You might notice here there's an element about the 45 engineers. That's my other business, which brings controls to the table. So a big part of what we do is it's about how we integrate the power solution to actually get the most out of it through good controls. And we'll just move forward. Right, so a lot of this was already touched on by Eric very nicely. What is BESS? What is it for? I think the point is there's a lot of bullet points on the list. All of them create opportunities, and when I talk about use cases and making a business case, each one of these bullet points creates opportunity. We're seeing, as was alluded to, it was really interesting to hear, the power companies are also looking for solutions to solve problems that we can help solve. So we've all got to work together to find these solutions. One of the big ones that is sometimes still overlooked is how we can actually help reinforce the existing network. Rather than just supply power to yourself or just sell power, it actually adds value to the network if we do it properly. Another one that I like, there's probably quite a few industrial people in the room. Are there industrial people in the room? So a bit of almost like a UPS or a backup power for your plant, and even smoothing out the peaks within your own facility. So when we're looking at a business case, we look at everything, including, what's your problems. Another thing Eric said is what is the problem you're trying to solve? What are we actually buying the BESS for? Is it just is it just an investment? We want to get a return on investment, or are we looking to improve our business in other ways? Right, so this slide, I'm just going to talk about this really briefly. So different architectures are important, and we put this in because people sometimes overlook it. And if we look on the slide on the right, there's quite a traditional approach. So a lot of people will start with solar on their roof, and they'll put some inverters in that you're just on the side of the wall, and these are little white boxes like we saw. And then they go, oh, we need a battery. So they put the battery in separately, and then we've got another set of inverters. So we're actually going from DC to AC, back to DC and into the battery and all of that. So what we try and do is look at different architectures, different solutions, and on the left here, we're actually bringing the DC from the battery, from the solar panels straight to the battery. So we're taking one step out of the equation, saves a bit of money. We're still doing a DC conversion. There's still parts and components, but it's more efficient. So we can talk to you about different architectures that will help and benefit the business case. Right, so quick example, business case. So there's a couple of numbers on here that are slightly, heroic, but we've tested them, and in certain scenarios we can achieve some very high return on investment. So if you don't believe these numbers, come and talk to us. We're happy to be challenged. But if we look here, what we're seeing is by using the BESS, we can really change the equation. So we're really shifting the dial completely in terms of the economics of a solar solution. So if we're talking a large solar, like mid to large solar, it's a high solar solution, the battery is the differentiator in our view. So you'll notice I talk to up to 24%. It's not always the case. It depends on your scenario. There's a lot of components that go into the model. So we have to look at everything in a holistic way. And, even if you've got half that, you're still doing very well as a return on investment. So the models are changing very fast in front of our eyes. There's plenty of people who want to invest in this technology. And what we have done, and we work with our customers, we bring in different partners so that we can pull together a complete business model. So sometimes we'll bring in an energy arbitrage partner to help actually buy or sell your power. And they'll do that, they'll work closely with you. One of the new models that's emerging quite fast is, people have plenty of capital and they'll actually fund and own the battery, and then they'll just supply the power to you. But you put it on your premise, they use your roof. Nice, lots of terms and conditions there. But, it's your energy, you use it first, but then you get the arbitrage, we sell all your excess, and we get a lot of extra benefit from that. And that's happening more and more every day. The other thing I've put at the bottom here is basically these sort of future opportunities. There's a lot of future opportunities coming. It's good to hear PowerCo already well into this by the sounds of it. But we can with the power inverter technology we're dealing with today, we've got very fast response times. We've got very smart metering. We're actually able to react very quickly to the stability issues in the network and correct for it in real time. So we can add a lot of value to industrial customers, industrial industrial parks. For example, we've got different users affecting each other, and we can put a big BESS in there with nice inverters, well controlled, and we can actually stabilise that network. There's a great deal of value there that's not quite, you can't quite sell it yet, but we're working on those models, how we get that value back. So the investment has legs, so we can do a business case that stands up today, and then there's more value we can derive in the future. I meant to go back. So just to point out, down the side of the building, there's the batteries there. So that's those are the batteries and inverters on the side of the building. So this case is in Auckland. So this is what some of the hardware looks like inside, just so you know. So over here we've got, these are the smart inverters that allow us to do that power control. So it's not just a battery, it's got quite a lot of smarts with it, and that's what adds a lot of value as well. So if we've just got a battery and a battery controller, it's limited to what we can do. So we try and promote the higher end, good quality inverters, which allow us to do very dynamic power corrections. So, okay. So if you want to think about a battery, there's a lot of things to think about. And I think the business case obviously is number one. And I think if you engage with people who have got experience, and there aren't that many around in New Zealand, we're starting to grow and develop that. We're quite early in this journey at the mid-level scale. So we've got a bit of grid, we've got a lot of houses, we don't have much in between. There's a big opportunity here to work together to find the business models that work. It could be actually collaborating between neighbours in an industrial area. You've got to work with the power company too. The customer we showed before, they're doing a lot of work behind the meter, which is what Eric talked about, where they're actually selling power to their own tenants. So there's sort of different models that can be grown and developed. What I would say is, if you're going to go to the lines companies, you need to go with a clear model and clear plan, and also maybe have done some work in advance, so that you're not just saying, "Oh, I've got this big connection I want to make. Can I turn it on tomorrow?" You've got a bit more, a bit more to it than that. So finding partners that can do the design, do the grid modelling is a good thing to start with. Things aren't quick to bring into New Zealand. Pretty much all the batteries are coming from China today. It is what it is. There's a lot of pitfalls in that, and making sure you get the compliance with New Zealand standards, getting the quality right, things like that. I think in the home inverters that's pretty well covered. There's a good range now that are pretty good, but getting into the next scale, it's a bit more open, and they're used to selling into markets all around the world at all different standards. So something to watch for is to make sure that you've got that supply chain right. That's something we've spent a lot of time on. Then there's a bit of so that's lead time and equipment. Then sort of one thing that we've not been caught out with, but it's been a bit of a hurdle for us a little bit, is New Zealand's got earthquakes. So you've got to think about how that shapes up. A lot of the batteries you buy off the shelf, big batteries I'm talking about, they're not really designed for seismic. So the battery will fall over and things like that. So we've got to look at those sorts of constraints. Physical location, civil engineering. We can talk about fire. Someone can talk about fire risk later, so you need to position them correctly. You need to think about the whole layout of the site and cable lengths and so forth. So there's a bit of planning and thinking. I put the logistics, and batteries are heavy because sometimes people want to put these in remote locations, and we priced a couple of jobs where the lifting capacity on an island, for example, it's difficult. So we had to allow to break the batteries down. One of those containerised batteries is close to 20 tonne. So, there's a lot of constraints to think about. So I've talked about the standards as well. So there's a lot to it, but just it's worth doing, is the point. I think what you need to do is start looking at all those questions of where you might want to put it, what are you trying to get out of it, what problem are you trying to solve, and then talk to experts and see if they can find that model that works for you. I think in most cases there is a model that works for you. So I think that's everything. Yep. That's my last slide, so thank you.
Thanks, Nick. So next up, we've got Ben Hume and Kevin Weller from the Beca team. They're here to talk to you about fire risk around batteries. So Ben is the
manager or regional manager for the Bay of Plenty for Beca, but he has a background in fire engineering. So he's not just a pretty face. He brings deep technical knowledge and insight into physical impacts of fire and human behaviour in emergency situations, built through extensive experience on complex projects in New Zealand and internationally. And Kevin is a senior associate fire engineer with our team here in Tauranga. There's a particular interest in emerging technologies and breaking down the potential risks and benefits these offer. He's also consulted widely with designers and regulators in the building industry, including recent involvement in helping develop industry guidance on the risks posed by lithium-ion batteries and electric vehicles. So welcome Ben and Kevin.
Thanks, thank you. Rightio, thanks very much. First up, great to see so many people here this afternoon. Fantastic to have everyone here and be able to talk about this, and thanks to the speakers so far. Really interesting and great to get those conversations going. So before we talk about fires, which tends to be quite emotive, reasonable to ask why Kevin and I are standing here talking to you about this. So Kevin, as Mike had said, is one of our lead fire engineers across the country, delivering projects locally, helping to write codes. He's currently the lead fire engineer and has been for many years to deliver the Dunedin Hospital, which is a very exciting project to get out. My background is I'm the regional manager for Beca here in town, which I absolutely love, but my background is fire engineering. What that really means is Kevin and I have spent far too much time in our lives thinking about fires, why they start, how they start, what happens when they start, how we stop them starting, how we put them out, and how you actually mitigate the risk. The aim of today is we just want to talk about some of the elements of fire that relate to batteries in particular, talk about some of the real risks of what that actually looks like, and then how we kind of manage that and how we deal with it to give a better understanding of it. Over to you, Kev.
So battery fires, and particularly lithium battery fires, have got a little bit of hysteria there, and Eric talked about fire is one of those sort of challenges out there. And it is. Lithium batteries, they burn quite nicely. They're quite unique in that they have all three components of what we call the fire triangle. They will burn very happily by themselves. Often, and the chemistries do vary, but the electrolytes will burn. That's your fuel. They will make their own oxygen. The electrodes often have an oxide layer in them, and when heated, they degrade and release that oxygen. And of course, heat, electrical, very easy to come by. The answer is, though, I mean, yes, the risk is there. The risks are not high. They are manageable. To get a good quality battery to burn, really you have to break it. You have to damage it. Electrically, poor charges, overcharging, charging too long. Mechanically, crash your EV into something, never a good start. Thermally, leave your phone in a hot car all day in the middle of summer. Manage these, and it's very easy to get away from that risk.
So we thought we'd actually start, we often talk about big batteries, and that's really what we're kind of talking about today, but we get a lot of questions about little batteries as well, and we'll class all the way up to an electric vehicle as a little battery. So we thought we'd put a bit of information up about that and a few snapshots of what we're really looking at. So when we're looking at small devices, I would probably bet money that almost every single person in this room is sitting there with a battery of some form or another in their pocket, whirring away, keeping their phones going or their laptops or iPads. All of that is actually quite a long way through our environment. You've also got scooters. We may have had people who have ridden electric scooters and bikes here, right the way through to electric vehicles and buses all the way up. A few interesting things about that. Yes, they can, as Kevin said, ignite and cause problems, but the risk is relatively low when they're high quality. So, for example, this is actually a photo of Kevin's house. I'm not sure he's super stoked with that, but that's great. We'll share these pictures. So Kevin's actually built himself a little bit of a wall in an area with some jib that he keeps his tools in case something does happen. Often it's when it drops, and then it's on the charger. The second graph starts to bring in that discussion around risk and what that actually looks like. So electric vehicles hit the news a lot, but actually if you have a look at it, the risk of a fire in an electric vehicle is actually quite a bit lower than a standard internal combustion or ICE car. They actually have about the same amount of energy that gets released from both of them, but it's in a different way and over a different period. But the risk is actually a lot less of it occurring. An interesting bit of information, if you took an electric vehicle that was fully charged and it had a fire, the total energy that it releases is equivalent to about a mid-size house. The difference is a house, you can have the firefighters putting it out and dealing with it and starting to address it. An electric fire, because of what Kevin was talking about and it's internal, much harder to deal with, so you get that burning and you get that constant release of energy. So lower risk, harder to put out.
So commercial, industrial and grid scale. These are the BESSs that our previous presenters have talked about. The single best risk mitigation with these BESSs is actually the control systems on board. As I said before, the batteries tend to be relatively stable. A good electrical control system that can pick up little electrical anomalies, flag them, and then your teams respond to those faults and actually listen to them, that gets rid of most of your risks. They do occasionally catch fire. I've got two images up on the screen through media. One was the Victoria big battery fire in 2021, and that really shook up the fire safety space. They had one of these big 20-ton Tesla Megapacks. It was undergoing commissioning. It caught fire. They sent 30 fire trucks there, about 150 firefighters, and it took them 3 days to deal with it. And that gave a lot of people the woolies, because that's huge. They tried all sorts of things to put that thing out, and put simply, you can't put water into those batteries, and those batteries don't want to stop burning once they get going. After quite a while, all they resorted to doing was cooling the surrounding batteries, stop that fire and that damage spreading, job done. The next one up there is the Boulder Combe fire, also Australia. We haven't had one in New Zealand yet, touch wood. The Boulder Combe fire, isolated rural area, I believe. They sent one of the local volley trucks out there, one truck. They spent, again, 3 days out there. But they didn't bother trying to put the fire out. They just cooled the surrounding packs. Job done. So that hype has really come down. In terms of how you actually set these things up, and Nikk talked about a bit of good early thought and how we plan them, that's really all it comes down to. If you're putting these units external, space them out. If one catches fire, the manufacturers tend to have recommendations. How close can you put these things to try and limit that spread, to give the firefighters the ability to stop fire spread? If you're choosing to put them into a building, there's more risk there. You can't put the fire out. A fireman squirting water on something inside your building for 3 days is going to cause problems. So you're looking at fire containment, firewalls. You're looking at possibly things like smoke venting and control, so those sort of heavy metal smokes aren't going through your building. And then in terms of the fire safety systems, and we see a lot of these going to market, more and more so now, there are specialist battery fire detection systems coming out. Many of you in the industrial space will be familiar with things like VESDAs, or aspirating smoke detection, a very expensive version of a smoke detector. And some of those are being tuned to deal with battery off-gassing now. There's some merit in that. That gives you early warning. But once your batteries started to fail and release those gases, it's probably entering that thermal runaway process. I'm yet to see whether that allows you to actually stop and save that battery. Fire suppression systems, we often hear people go, it's fine, I've got an inbuilt fire suppression system in my BESS. Those systems are there to deal with the electrical fire, not the battery fire. Many of these fires start within the electronics, within the switchboards, and those suppression systems will deal with those. That will hopefully stop it getting to the battery, but once the battery is involved, you're still you're in for a long few days. And finally, firefighting. As I said, firefighters are on the edge of these things. Many of them haven't looked past the Victoria battery fire. Be wary talking to fire service. It's good to talk to them. It's good to help them make a plan in case something goes wrong at your site. But they are still seeing what's in the media, and they're responding to it on that basis. Things like good water supplies are really good access, and a bit of a plan for when they come. It doesn't need to get too exciting.
So while we're focused on talking about batteries, we get a lot of questions about solar, and with everything that's going on at the moment, there's a lot of discussion around increasing that. So there's a few thoughts that we'd share on that. So solar panels in themselves aren't actually that combustible. They don't add a lot of fire load or a lot of risk. Again, it's the electrical elements that tend to pose a problem. What's the insulation selection on the cables to get there? If you put them on a field, how much combustible material is below it? In Australia, they're out in the desert often or dry spaces, so they tend to keep it very clean. Here, we'd keep grass to about 15 centimetres. Once you go above that, the height of the flames, if it does occur, become harder to control. So it's about controlling those levels. Buildings are slightly different in that you've often got them strapped to the top of a building. And again, the risk is not the solar panels. The risk is actually you get an electrical short and that starts a fire within the building. And so it's being able to manage that. It's making sure that you've got isolations for the fire brigade to be able to shut it off when they get there. There's an example where the fire brigade came into a fire one night. The building was on fire. The fire brigade put the fire out, dealt with it. The sun came up in the morning. The panels started working, down to a short, and restarted the fire. So it's really being aware of what's going to happen with that, the energy flow that's occurring as it goes through the building and how that transfers and how you shut it down.
So really simple solutions like the warehouse, a sign on the fire alarm panel. There are solar panels on the roof. Done. When we put these projects through, you want to do them with confidence and what those sort of hurdles you're likely to hit are. There is a lot of myth around the idea of solar panels and lithium batteries, and really mitigating this risk is around that storytelling piece and just acknowledging how we're managing that risk. It's not too bad. From a building consent perspective, there isn't anything within the fire codes around batteries or solar panels. Think it through and be sensible. Some of the councils are wary of it. So again, understanding that risk, being able to tell that story. We've been involved in a couple of resource consent type projects where there's been a lot of pushback against solar farms and whatnot. Neighbours, fire service and others just not understanding that risk. Just work on this. Yeah, it's talking about those risks, talking about the how we manage them. There's a lot of really good information out there. There's also a lot of really exciting YouTube footage that goes the other way. So it does require an active approach. Where it lands, I guess, yes, there are risks. There are risks with a lot of energy stuff. LPG, petrol, they all burn nicely. Batteries can have a risk, but it's not a high risk. Be thoughtful about it. A bit of early on good planning. The mitigations are not onerous. It's certainly not a barrier. And I'm trying to, at the moment, put solar and batteries on my house. So here we go. Thank you.
Thanks very much.
Thanks, guys. Hopefully that gives people a bit of assurance that some of these technologies, yeah, there's risk with any technology, but actually if these things are manageable. That's all right. So next up we've got Hendri Barnard from our industrial team. So he's a process engineer with experience in delivering energy transition accelerator studies, decarbonisation concept studies, and emissions reduction pathways for clients across New Zealand. And one of the topic he's going to talk to you about today is a similar topic to what we've just been talking about, but rather than electrical energy storage, it's about thermal energy storage. So I'll pass now over to Hendri.
Thanks. I did not bring my laptop, so I would need to reflect back to my slides. Apologies for that. So we've heard a bit about how to store electricity, and the question is, can we store other forms of process heat, process energy? And the answer to that is yes. Thermal energy storage systems does exactly that, and thermal energy storage systems has been around for quite some time. The three key takeaways that I would like to leave with you today is just to understand what is thermal energy storage systems. I'm going to focus a bit on high temperature thermal energy storage systems, as this technology has been in the media over the last couple of years. So I'll dive a bit deeper into that, and then give you some information. What are the questions? What is the good information that we need to have when we're building a business case for thermal energy storage, whether it's high temperature thermal energy storage or one of the other technologies available? I like to think of thermal energy storage systems as a dam. After the good explanations around batteries and what batteries do, I might need to change that. But like a dam, it receives inflow from various rivers. The dam itself then buffers this, all the water coming in, and then that is controlledly let down into the consumers of that water. Similarly to that, thermal energy storage systems absorbs either heat energy or cooled energy from the site, and then stores that energy and then gives that energy off when the process requires that. The rivers, in the sense of a thermal energy storage system, can be cheap electricity. It can be waste heat from other processes, and it can be on-site solar generation. So what is industrial cases of thermal energy storage? As I mentioned, some of these technologies has been around for quite some time. I just think it hasn't been called thermal energy storage. And the first 4 examples that we have there is generally considered as good practices in modern day engineering to help with energy efficiency, balancing the loads between industrial heating and industrial cooling, and how do we optimize those systems. So I might just reflect on the chilled cold water storage process and refer back to the dam analogy. So in this case, you might have, think of off-peak electricity pricing. It's generally during the night. Your on-site refrigeration system is not under heaps of pressure because of the ambient temperature that might be lower as well. And you then choose to produce excess refrigeration during this time because of the electricity that is at a favorable rate. So your dam in that perspective would be your tank storing your refrigerant, and then when either the prices peak or your process demands that additional cooling, you can then let that energy out and effectively reduce the cost of what your cooling system is operating at. The one that I've highlighted is the high temperature energy storage system. As I mentioned, this is something that has been in the media a bit more frequently, and the next slide has a couple of licensed technology providers, and there has been a system implemented in Australia around this. But this technology is really focused around that really high temperature industrial applications. I'm talking 250 to 1,000 degrees. Generally, these systems are really hard to transition away from fossil fuels. You need that heat of combustion to actually supply this energy. And there has been quite a bit of work done in this space with high temperature thermal energy storage systems. So as you can see on screen now, this is just some of the licensed technology providers that we have been dealing with. It all looks quite different. All of these licensed technology providers will have their own proprietary information from the material that they select to actually store the heat, to the way they integrate that heat into how do they charge the systems, how do they discharge these systems. There's really quite a big variety, and every every licensor develops something that's a little bit more bespoke than the other ones, but I'll try and cover the basic principles of it. The one that I find quite nice is, where's this going? No, it's not going. The one that I prefer, that I quite like, is the Energy Nest example, where you can see the concrete tubes. The concrete sleeves with the tubes in it, and that concrete material is actually the thermal energy. Is it working? Doesn't look good. That material is the material that actually absorbs the heat, holds the heat, and then when the process demands it, it actually gives off that heat then back into the process. I seem to have broken this. Oh, the battery is dead. Sorry about that. Please don't red petal me. And we're back. Awesome. Oh, yeah. No. Oh, yes. Okay. Cool. I'll try and go through this. So One of the challenges with the system is because it needs that really high heat. It doesn't suit well for waste heat integration. Waste heat is generally at a lower quality, so you need something to give you that. If you're designing a system that needs to supply heat at 800 degrees or let's say 500 degrees, you need to charge it at a temperature higher than that to get that fast charging. So most of the systems that all of the systems that I've shown previously, it has to have some form of electricity connection. Whether that's grid connection or on-site solar generation or a combination of that. That electricity is then goes through the electric heaters that is integrated into the thermal energy storage material, and that then heats that material to the desired temperature. That energy is then stored, and when required, that energy is then released through heat transfer into the process. Just a couple of things pointing out on the slide. So depending on which technology licensor you're talking to, sand, concrete, carbon blocks, salts, that's all the materials that they use to store the energy. And then a lot of them is quite flexible on the process supply side. So it can be hot water, steam, thermal oil, and I missed one, air, hot air as well. And is this working? Yes. Oh, too far. So some of the conceptual cases that we have reviewed at Beca, and again, this is conceptual data because of the commercial sensitivity. I can't share the actual data, but we've been approached to have a look at how these systems could potentially be integrated. One of the scenarios that we considered was, can we charge the system during off-peak electricity, when electricity is cheaper, and then use that to run throughout the system during the day? Thanks. Okay. So what I've got at the bottom here is just the teal at the bottom is the actual process heat demand. The yellow is the charging. Sorry, you can't see this side, sorry. The yellow is the charging of the actual thermal energy storage system. Again, the idea with this system was, can we reduce our process heat through charging these systems during the night and then discharging throughout the day? So you can see the charging happens during off-peak rates. We're charging all of the entire site demand, and then we're supplying that when the process requires that. In this instance, the business case did not quite stack up because of 5 minutes, because of the electrical infrastructure work that was required. You can see the system needs to charge 3 times faster than what it's discharging because you only have 8 hours to charge the system. I might go a little bit quicker through these, sorry. The second scenario was on-site solar integration. So company has solar panels. Can they use the solar panels to charge the thermal energy storage system and then give off that heat into the process? Sorry, the client did not have solar panels at this point. So again, similar to that, teal is the process load, yellow is charging the thermal energy storage system linked to solar. We had a look at the amount of solar that they could have available and size the thermal energy storage according to that. And in this case, it was a 50% offset of the process heat demand. This one also didn't quite stack up because of the additional cost of the solar panels, the thermal energy storage system, plus there was some additional work on strengthening the building to actually accommodate for the additional weight of the solar panels. The most intriguing one to me was a client that has solar panels already, and they were whenever they had excess electricity generated from site, they would gift that back into the local grid. They asked if a system like this could potentially help them use more of the electricity that they're generating on site. So what I have here is, and I should have had days in here, sorry. So that's a Friday. They run a 5-day operation, so they run Monday to Friday. You can see the teal is the peak loads of the facility on a Friday. They don't run over weekends, so there's a little bit of load that's still trickling into the process. But the benefit of this one really is this excess in energy that you can generate over that weekend, capture that, and by implementing this into their system, they could get to start up on a Monday and get to about halfway through a Tuesday before they had to commission their process heating devices again. So it basically gave them a day and a half of free operation. I can already hear Nikki mentioned thinking batteries because it's linked to solar, and that is the key that we need to work through, is which one is still better. So does high temperature thermal energy storage stack up? The answer is yes, in certain scenarios, like anything. There isn't, unfortunately, a one-size-fits-all in all of these. You are still reliant on the electricity grid, so you are still subject to electricity pricing. The quality of the energy stored is just energy for process heat, where the benefit of a battery system is you can apply that electricity more widely. It doesn't need to just go into process heat. Waste heat integration I've touched on, because of the temperatures required. Waste heat integration into these systems is quite limited. And then we've covered the charge and discharge as well. Generally, if you have to do it in peak or days when you during the daytime when you have sun, you're charging a lot quicker than what you're actually discharging. Did I break this one? Some information required when considering one of these options as well. You really need a clear understanding of your heating demand for site. This is somewhere where Beca has been doing quite a lot of work with ECA around understanding site thermal loads, understanding site electrical loads, understanding cooling loads. And once you've got a real clear picture of that, you can see if this technology is something that will work for you. You need to have a bit of a consideration around the temperatures and the tolerances and the ramp rates in the process. It might require specific hold times and that. Electricity pricing. So what is your electricity tariff pricing look like? Do you have a really favorable peak versus off-peak price that you can leverage? And then if you do have solar integration, what is your site's potential solar integration to try and offset some of that electrical demand? In conclusion, the thermal energy storage has been around for quite some time. As I mentioned, a lot of it is seen as good design practice. However, high temperature thermal energy storage is something that is constantly developed. Just in the 4 years that I've been looking at it, it's gone from really bespoke, big grid scale type installations and to more how do we get this technology introduced at smaller sites? How can we get those containerized and actually work in those spaces? It is still reliant on electricity, so you are not completely disconnected from that, but it does tie in fairly well with solar PV on-site generation. And that is me.
Thanks, Hendri. Right now, our next speaker is online. So we've got Adeline Bartoletti. So Adeline is an industrial and scale-up engineer with 20 years experience, including 12 years working on active sites across the European industrial sector. She has led integration projects with across the full project life cycle, from front-end design and procurement through to site commissioning, on technologies including carbon capture systems, combined heat and power units, and facilities like Beca, Alstrom, and municipal clients in France. So she's the CEO of Kelvius, and she applies that operational background to develop heat upgrade technology built around real constraints of industrial sites, operator workloads, safety regulations, and spatial limitations. So yeah, but we welcome Adeline to the virtual stage.
Okay, so thank you. I think this is a very good transition from what Hendri presented. And now I would like you all to imagine industrial sites where you can have thermal energy storage, just like you have been presented, and a technology like Kelvius, because we could increase industrial sites resilience by operating different types of assets like these two combined together. So I will pass super quickly to the first bit of my presentations because I don't want to open doors which are already open, and I would like to focus on what matters here. So just before I go further into this presentation, so Kelvius is a deep tech startup, so industrial startup, which is currently developed in Wellington. You will not find a website of Kelvius because we are playing stealth on purpose in order to protect the IP. And so we exist now for 2 years. When I founded Kelvius 2 years ago, the tech had been proven at a lab scale. And since then, we have brought it to test rig scale. And we are currently designing our first pilot plant, which will be integrated into a real site in New Zealand. So what are we trying to achieve here? So this is not new for you. 40% of the global energy is consumed in the industrial sector in order to produce industrial process heat. And amongst those 40%, 30% are wasted globally. So here we can act with 3 steps. We can recover waste processes streams. This is not new. This has been done for the last 3 centuries in the form of heat exchangers. We can store them chemically. And here I say this is an option. Why? Because currently 90% of our potential adopters do not care about the storing capacity for what we are currently trying to do, because they run 24/7 continuous processes. More critically, we are able to upgrade these waste processes streams. How? This is done with our chemical process, and we are able to provide a temperature lift because we run a batch system which is able to upgrade these waste processes streams so that we can re-inject them at the inlet of the manufacturing processes. So right now, when you think about process heat, it is done with a linear way. Basically, when you operate an industrial site, you purchase primary energy, natural gas, coal, electricity, biomass, whatever you have on site, and you waste heat in the form of these exhausts. So when we integrate our technology, we can show that we can put a value back on the hidden value of waste processes streams, and we can re-inject them at the inlets of these manufacturing processes. So this is what we are currently developing. So we have our own sets of equations which have been conceptualized out of a PhD at the University of Auckland. And so we have our own software which is able to predict the temperature lift that we could provide for a certain site. Why do I say that? Is because we rely on the water content of the exhaust of these industrial sites. And therefore, the temperature lift that we can provide is completely dependent on the parameters of these exhausts. So in terms of temperature and humidity ratios. We have our own proprietary materials. So right now, we rely on an existing material that we have repurposed for our own application. We are currently characterizing its performances so that we will be able to develop the next generation of these materials in order to increase even more the performances that we could bring on the table for our potential adopters. We are developing the vessels which are able to host these proprietary materials. So we rely on fixed bed reactors where we can have gas-solid reactional system. As you can guess, so this is a batch system that we operate. And so we are able, with our control system, to convert this batch system into a continuous system. And therefore, we will be able to deliver continuously some heat to the industrial sites. So right now, we can say that, and this is not me saying it, this is one of my potential adopters that has done this work alongside myself. Kelvius technology is currently the only one which does an open loop, thermally driven heat transformer with water as a refrigerant. Why do I say that? So we rely, as I said, on the gas solid reactional system, and the refrigerant is the water which is embedded into the exhaust of the industrial sites, so the waste process heat streams. So we call that an energy multiplier because we can provide temperatures up to 350. So if you do a super quick research, 350 degrees for certain sites corresponds to basically 80% of the process heat temperatures that are required in the world for the main markets that are process heat users. So food and beverage, chemicals, and pulp and paper. So we have already proven for these three markets that we have a topic and that we could bring an IRR, which could make sense for them. And so the temperature lift that we could provide for these specific sites starts at 70 degrees. So this is the low range of performances that we can bring, and we could go up to 200 degrees in terms of temperature lift. So here we use another way to explain why we said it's an energy multiplier with a spread dryer. So we work with dairy factories, dairy companies. And so you can see here what we could bring in terms of temperature lift. So the blue that you can see at the right end is what they need to purchase in terms of energy in order to send a certain stream of air at 220 at the inlet of the spread dryer in order to produce milk powder. So this is, you will see in the next slides, we have studied an existing site which produces 16 tons per hour of milk powder. And right now they need 11 megawatts in terms of process heat at the inlet of the spread dryer. Because we are able to recover and upgrade the exhaust of the spread dryer, we can say that we can provide a temperature up to 150, and I will show you in the next slide how it could work. So 150 is not enough to cover what they need because they need 220, and we would be able to provide between 50 and 75% of the airflow rate that they need at the inlet. Basically, we act as a baseline of a process heat production, and they need to top up in terms of flow rate and temperature. So this is how it could work. So as I said, spread dryer, 16 tons per hour of milk powder. So right now they run a natural gas boiler which produces steam at 237 degrees. And they convert this heat into hot air at 220 with classic heat exchanger. What they release is humid air at 70 degrees. So here we are able, as you can see on the right, to recover these waste process heat streams and to integrate Kelvius technology. So here we divide the flow stream into two streams. One on the left goes to what we call the charge. So here we convert the waste process heat stream into dry air in order to charge our chemical component. In order to charge, we need dry air. So this is why we rely on a heat exchanger as well. On the on the right side, sorry, this is where we trigger the discharge of the heat by sending directly the waste process heat streams, so humid air at 70 degrees, inside our fleet of reactors. So this corresponds to what we call the discharge. As you can guess, charge is endothermal and discharge is exothermal. So the temperature lift that we can provide is between the inlet of the reactors being discharged and the outlet. And we still have to plug a heat exchanger again in order to convert the outlet of the reactors into hot and dry air because the humidity content of the outlet of the reactors is still too high to be sent directly into the inlet of the spray dryer. And as I said, depending on the cases that you can operate, you could provide a temperature starting at 110, optimized 150, depending on what are the mixes of waste processes streams you can get on the site. And we can provide a flow rate delivering between 50 and 75% of the total required. So this is an example of what we can achieve with our test rig that we are currently operating in our premises in Wellington. So this is a screenshot of what we have done. So the pink curve that you can see is the inlet of our reactor that we are operating. So the inlet, as you can see, is at 75 degrees in, and the rest of the colors that you can see corresponds to thermocouple, so temperature measurements that we have embedded at several levels of our reactor. So you can see the how we can have a gradient of temperature alongside the height of the reactor. So the blue ones are at the bottom of the reactor, and the black one that you can see at the right corresponds to a thermocouple, which is outside, so just above the last layer of reactors. So here we can prove that we can achieve 115 degree of a temperature lift for half an hour. So the difference between 70 degree in and 185 out. So when we do currently an imaginary exercise where we take the performances that we have proven at our test rig scale, we can try to do some feasibility studies and IRR calculations. So for this specific case, which is a real site, they require 11 megawatts in total demand of heat at the inlet of the spray dryer. We could abate between 2.5 and 4.5 megawatts in terms of heat, which is recovered and upgraded. It would require something like 12.3 million New Zealand in capex. We can have a bit of OPEX as well for electricity consumption of our auxiliaries. And basically, we have proven with them that we can achieve an IRR between 28 and 45%. In terms of economics, so I've done an exercise where I have calculated the LCOH of Kelvius technology along the 25 years of the installation lifespan. So this is something that we consider. It includes absolutely everything, including material replacement, because this material, as you can guess, has a plateau and then starts to decay after a certain number of cycles. So this is something that we have taken into consideration. We have taken into consideration as well the electricity consumption of our auxiliaries, some maintenance, and some overhauls every 5 years. So when we add up the capex and the opex over the 25 years of the installation lifespan, this is the type of LCOH that we can reach, and this is for New Zealand and Europe. In terms of where we place ourselves, so here I've used KPI, which is the electrical COP. So electrical COP, basically what I take in terms of equation is the ratio between the heat output, so what we can provide in megawatt, divided by the electricity consumption. Basically what we can sell divided by what the site will have to spend. So I do not consider the thermal COP right now because obviously the thermal COP is below 1. Otherwise, I would go against the third law of thermodynamics, and this is wrong. So thermal COP of Kelvius technology is below 1, but the electrical COP, where we consider only the parameters which have a value, so heat output divided by electricity input, we can prove that we can achieve an electrical COP between 15 and 35. So we have several markets that we have started to work on. Of course, food and beverage and drying applications is the strongest for us right now. We are already speaking to some potential adopters in New Zealand, Australia, and we are currently starting in Europe as well. In terms of deployments, so this is what we are currently targeting. So as I said, we have started the design in terms of process and mechanical design of our pilot plant, which will be integrated into an existing site in New Zealand. And then it will enable us to trigger the next stage of capital raise, which will enable us to work on the first of a kind. And I still expect the first of a kind to be deployed in New Zealand. So here you can have an overview of what is the test rig that we are operating in Wellington. So it is, we are currently operating in a very big warehouse slash a big garage. So the reactor that you can see in front of you is able to host 50 liters of material, and the rest of the machine on the left side is able to replicate all the parameters that we could ever encounter. So I think this is still true. I haven't bumped into a site which parameters we cannot replicate with our test rig. But basically, we are able to replicate anything in terms of waste processed streams, so hot and humid air, at temperatures up to 350, with the humidity ratios that we can choose up to 100% of relative humidity. We can even simulate saturated steam under vacuum. It could correspond to the outlet of multiple effect evaporators, for example. And yeah, so we can even simulate a natural gas boiler flue gas. So we can simulate them all. Thank you for that.
Thanks, Adeline. What we're going to do is might have a couple of questions for Adeline first. So if we could grab a microphone. And then once we've done Adeline's questions, then we'll go on with the in-person question session. So I'll just grab the microphone. Firstly, has anyone here got a question for Adeline? No? Looks like you're off the hook, Adeline. Thanks very much. That was really interesting, and it's really exciting to see what could be some, quite game-changing technology being developed here in New Zealand, with some applications to benefit our industries here too. So, thanks very much, and all the best.
Thank you.
Right. So we're going to do a bit of an experiment for this last bit. So as sort of mentioned before, part of what we're trying to achieve with this series is to reduce that uncertainty. So hopefully this session you've learned something. So to help understand a bit about the various different technology options, but also who to talk to if you've got questions about these things, and just some people you might be able to talk to. There's a lot of people in the industry, and probably some in the room who are also experienced in these areas. So the other thing we want to do is that connection and that collaboration. So the next session, we'll see how it goes. It might not be, what we're going to do is just to break the room into probably 3 groups. So we'll have 3 corners, and we're going to the presenters to go to one of those corners. And then if you've got an interest in that technology in particular, please move over there. And we're going to get you to introduce yourselves. So just going to go around whoever's standing there. Please just give your name, organisation you work for, and just a one-liner on what's a energy project or initiative or topic that you're either doing at the moment or you're interested in. So that the idea being is it's just a little bit of an icebreaker before we break for drinks, so that if you spot if there's another person, another organisation who's actually working the same thing as you, then actually you can make a beeline for them and catch up with them. They might be having expertise in a certain area that is of interest to you. So the idea is just to have a bit of a soft icebreaker before we then sort of organically move into drinks. And also at that point, once we've done a bit of an introduction around the room, if you could just, if you've got any questions for that particular presenter, please ask them. So maybe a bit of a forum on the specific topics. And if you want to move around at that point, go and talk to someone else, please do. And if you just want to grab a drink, just go and do that too, because drinks will be served and there'll be food coming around very shortly. So what we'll do is, Kevin and Ben are already over here, so we'll get if you want to talk about fire or anything fire related, please come over to this corner over here. Nikk and Eric, where's Eric? There. So maybe if you guys go to the back of the room. So if you want to talk about batteries or BESS, please go towards the back of the room. And Hendri will get you to come over the front left here. We'll see how this goes. So please do just speak up, introduce yourselves, and and we'll move to drinks from there. But thanks very much for coming. I hope you found it enjoyable and interesting, and you've learnt something. And we welcome your feedback as well. So if you've got this is the first of a series. If we can make them, what are the bits you liked? What are the bits that actually you would like to see differently in a subsequent event? We appreciate your feedback to make these as valuable as possible for you. So thank you. And a round of applause for all the speakers.